Okay. Sorry for the delay in the start of class, but I guess we're better late than never. We've got a homework due tonight. I think it's homework 6. Look at that, homework 6. After homework 6, we're going to have homework 7. And after homework 7, we're going to have the midterm. I'd like to try and schedule the midterm so that it happens prior to the Easter break. I think we're still having an Easter break, aren't we? And looks to me like we've got our work cut out for us. This is sort of where I'm at. I'm thinking we'll have homework 7 due for digital design. And then we'll have homework, well, I guess we won't have a homework 8 due. We'll do a homework 8. What I'd really like to do is get the midterm done over here on the 29th. And so I'd like to make that for CR, well, I don't know what we're calling it nowadays. Whatever we're calling digital design 1, I lost track of the course number. I got to look it up. Everybody changed all the course numbers. So that's the plan. And the reason why is that if you look at April, you'll see that there's like an Easter thing going on over in here. And so I wanted to try and get it done before the Easter recess. That'll give you guys time for other classes. So that's the plan. We won't do homework 8. We'll just go straight into midterm review. And the midterm will be a mashup of the prior homeworks. So that ought to keep people in good stead. The homework 6, that's due today. Tonight, actually. And so what I thought I'd do is, and I think we've been over this pretty much, but maybe people have questions about homework 6 or they want to see something else done with homework 6. Otherwise, I will put homework 6 to bed, so to speak. Any questions about homework 6? Going once, going twice.
Let me just check.
Number 2, please.
Number 2.
I had the same question.
Oh, okay. 2 people with the same question. Must be important. Let's see. Edit the test. Let's see. Go in there. And homework number 2. I'm sorry. Homework number 6. Problem number 2 is what choice best describes this circuit? Wow. Okay. So I'm going to redraw it. Okay. And it's got 4 outputs. Okay, so here's a blank box. And it looks like there's an enable. So what does that look like to you?
Decoder.
Yeah, that's a 2 to 4. There you go. So that's a decoder. And here's the outputs. I think they label them 0, 1, 2, and 3. And so what you can do, if you like, is you can look at the truth table for the decoder. Right? So here's S1, S0. We'll do it in binary order. And now here are the outputs, which we will describe as F0, F1, F2, F3. So there's 4 outputs. And now what you can see is that if you select 0, 0, that's a 1, and everything else is a 0. Hit 0, 1, then that's a 1, and everything else is a 0. If you hit 1, 0, then it looks like that's a 1 and everything else is 0. If you hit 1, 1, then this is a 1 and everything else is 0. It's a very symmetric sort of thing, you see. It's going down the main diagonal. Or is that the secondary diagonal? Just that's a secondary diagonal. But in any case, it'd be the main diagonal if I numbered the functions in the other direction. And then as it happens, oh no, that's right. 1, 1, 2, 2, 3, 3, 4, 4. Yeah, it's the main diagonal. So now if I were to, I don't know, write the canonical sum of products form for F, I'd say F0 is equal to sigma M of, and then number your truth table, 0, right? It's the only one that makes it true. F1 is equal to sigma M of 1. F2 is equal to sigma N of 2. F3 is equal to sigma M of 3. And that is a canonical sum of products form, shorthand notation for the 4 functions that are embodied, if you like, in the truth table. Moreover, we can find an implementation. This would be S0, S1, both inverted. We can go S1, S2 if you want to keep it sort of consistent, right? S1, I'm sorry, S0, S1 in, or S1, S0 if you like. So that's a 0, that's a 1, so this is primed. And then if you look at 2, the least significant bit is primed. And if you look at 3, none of them are primed. And that represents the, how you can call it, implementation for the 3 functions which are embodied inside of the 2 to 4 decoder. So then the question is, well, how can I implement these things? We can say, well, okay, there's a few ways we can do it. Let's assume that we have S0. And then if you, maybe it's better if I do S1 first. S1, and then we take it and we run it as a bus. We take the bus out, give it a little inverter, and then we call this S1 prime. That's another bus. And then we have S0 and S0 prime, and we run that down as a bus. And then we get ourselves, right? And so now you've got S1, S1 prime, S0, S0 prime. And now all you really need is like some AND gates, right? So here's your AND gate, and the AND gate gets tapped into S0 prime and S1 prime. So it goes here, and then in here. And here comes another one. That'll be output F0. And now this one's going to have inputs of S1 prime, S0 prime. And then this one will have, that'll be F1, and this will be F2, and F2 is going to be S1, S0 prime. And you'll have F3. And that's going to be, according to this, S1, S2. I'm sorry, S0, S1. So S0 is going to be here. S1 is going to be here. And that is how you implement that. And so now you've got basically all the product terms available. And now you can tap into those product terms if you like and make a combination of different functions. But this is what you get from the decoder, all possible product terms, which is really cool because now with all possible product terms, this is how FPGAs work. This is how field programmable gate arrays work. You just program either with a fused or an anti-fused device, depending upon whether you're using an Altera device or a Xilinx device. You just tap into the places where you want a product term. And so then what this does is it says, oh, I've got a new function I'll call G, where G is equal to, and then you can put it in sigma M, and then number your product terms. But they're already numbered because it's F1, F3, and so you just throw in 1, 3. And that is a simple implementation. Now all you need is more AND gates, and you can add more functions. And you can have up to 2 to the 4 functions, or 16 different functions. So that's cool, because if I add 1 bit over in here, then I'm going to have 8, and I'll have 2 to the 8, or well, some big honking number of functions. How much is that? 256, 2 to the 8. Big honking number of functions, all because I have all the product terms from my decoder, which is cool. And you can implement it all without K-maps, which is perhaps a relief, especially when you get into the higher number of variables and you need a lot of functions. Now, what was the other question that somebody had? Or first, did this answer your question? Went into some more detail, but I wanted you to.
I had a question on number 7, if we could run through that really quickly.
You betcha. Right. Yes, sir. Let's see, what do we got here?
A lot of drawing.
Yeah, all right. So here it says, this is a big drawing. It really is a big drawing. I don't want to draw this. I don't want to draw this. Let's see. Okay. How many inputs on a BCD decoder? Well, let's take a little sidestep and say, what is BCD? What is BCD? Isn't somebody going to help me answer that question? Is there sound? You can hear it, right? Everybody can hear me? I guess it can at this point. Somebody wrote this. Any takers on that one? This is from your reading. So BCD stands for binary coded decimal. And I'm guessing that if you don't know what it stands for, you probably don't know what it is. That's a fair guess, isn't it? I'm trying to change pens over here. So if you have numbers 0, 1, 2, 3, 9, these represent your decimal. Oops. Yeah. These represent your decimal digits. And your binary encoding for these things radix equals 10, also known as decimal. And this is the BCD, which is radix equal to, but limited to only those decimal digits that require representation. Anything beyond this is not decimal. In other words, if we were A through F over in here, we don't actually have to care about the representation there. Moreover, the reason you want to have a BCD encoder is because you want to drive something that's going to essentially display the decimal figures. So the BCD decoder knows how to drive a display, you see. And so what you want to do is you want to be able to say, well, how do I make a 9? And the BCD decoder will do something like this. And it'll also help you make a 1 and a 2 and a 4 and all the other things that you need in order to be able to represent the decimal numbers. It'll skip the A through F. And so as a result, a BCD decoder needs to be able to drive segments A, B, C, D, and E. See, so when you're looking at, and I think he might even have F in there. Does he have F in there? F and G. How about that? So he's probably got some sort of a decimal point for F, and I'm not quite sure what the G is for. Perhaps there's another segment somewhere I'm not aware of. So his, that would be an 8-segment display. This is 1, 2, 3, 4, 5, 6. How many segments?
Could there be that rather than one segment making up the outside, it's like 2 separate segments making up, like where D is, it'd be 2 separate segments?
That's probably right. I think I may have forgotten that these things have 2. So it goes like this. Yes, yes, yes. That's it. Thank you very much. So then it would be A, B, C, D, E, F, G. And I think that covers them all. There's no decimal point in this. So that would be a 7-segment display. 1, 2, 3, 4, 5, 6, 7. And now it becomes a little bit easier to do things like this. And make a 2. Or make an 8, which is obvious. Make a 1, which you can do. Or make a 7. So you've got all your numbers in the basic 7-segment display. That's probably close to the display that you have on your DE2 Quartus boards if you guys are going into the lab. So that's typical. You'll want to be able to take your decimal numbers and convert them into something that will drive these segments. And that is what a BCD driver does. It's a 7 or 8 segment LED display driver. Usually it's something like a 74447 or similar. So how many inputs are on a BCD decoder?
So it's going to be 8?
Well, that's outputs. You need the
Oh,
8 outputs to drive your segments. But the inputs, you see, you need 4 inputs. You need 4 inputs for the 4 bits.
Oh, okay. Thank you.
So that's the bird's eye lowdown on the BCD decoder caper, whatever that means. What other questions might you have on homework 6?
Can we do number 19, please?
You bet. You bet. Let's see. We got number 19. I think it's time for a fresh piece of paper. Just a minute. Here. All right, so the story is, given the 4-to-1 multiplexer, if C1 equals 0 and C0 equals 1, what would the output be? So here we go. Let's redraw the whole thing so you can see it. Now somebody said this is a 4-to-1 multiplexer, so it's got 0, 1, 2, 3, 4 inputs. They call it a 4-to-1 mux. It's got 1 output and it's called M. And then it's got 2 inputs, which are selector inputs, C1 and C0. And someone said the input is going to be C1 equals 0 and C0 is equal to 1. So if I know how multiplexers work, what that means to me is that the multiplexer is now selecting input 1 because there's a 1 on the selector input. So then it says here, well, the inputs are X0, X1, X2, and X3. So if we're selecting input 1 and X1 is being used on input 1, then M must be equal to X1. What do you think of that?
Oh, okay, that makes sense. I think I was thinking too much into it.
The other way you can do this is that you could I don't know, reverse engineered the circuit. You could do that. I wouldn't, but the way it's written, you've got inputs which are wired to C0 prime, C1 prime, X1. And then another set of inputs which are wired to C0 and then C1 prime. Right. And you can sort of see how the numbering is here. 0, 0, 0, 1. The next one is going to be 1, 1, which will be, sorry, 1, 0, I would guess. 1, 0. And then that would be, no, we did that. 0, 0, 0, 1. Yeah, 1, 0, like this. And so then that would be looks like I'm backwards here. Oh, that's right. That's right. And then so this would be C0, C1, and then that would be primed. And then you have 1, 1, C0, C1. None of them are primed. And then this would be X2, X3, and X4. So that's a way to implement a multiplexer, then take the whole thing and run it into an OR gate. And now you can see how your selectors are enabling selectively individual AND gates, which will effectively enable something like the input to pass through to the output, which we can call M, as indicated in the diagram. So that's a way to go. I don't know if that answers your question. I hope that answers your question. That was question number.
Yeah.
That's good.
Thank you.
Sure.
Excuse me, Professor.
Yes, sir.
I'm not sure if you went over this like before, but I noticed like on the homeworks there's on Blackboard there's multiple attempts. Are we allowed to do it again if we didn't like our score?
Yeah, you get two chances, and the way Blackboard grades is you get the higher score of the 2 chances. So you can do a multiple submit.
Okay, thank you.
Sure. That's the same for the midterm, by the way. So when you come across the midterm, I don't know if you want to, but essentially you could record, you could print the whole thing, do it all offline, then restart the midterm, and then key in your answers. And then when the answers come back to you, you can then modify your answers and say, oh, well, it looks like I got one wrong, and work through it again, and then you get the better of the 2 scores. It's a rather long midterm, so I do not recommend you wait until the last minute on that one, but can't do it until we're finished with homework 7, obviously. Because homework 7's on the midterm. Any other questions about homework 6?
Number 18.
Number 18. How many AND gates are required for a 3 to 8 demux? A demux is the same as a decoder, right? So what we saw before, I think we kind of beat a dead horse on the last one. How many AND gates did we need for a 2 to 4 decoder? 1, 2, 3, 4. So if that's true, how many AND gates do we need for a 2 to 8? A 3 to 8 decoder? It's like, well, 3 to 8. If 4 outputs require 4 AND gates, then 8 outputs require how many AND gates? You're killing me here with
8.
silence. 8, thank you, thank you. Yes, that's quite correct. So you will need 8. And you can devise their inputs just the way we did here. There's probably a compelling argument that we should do it again, but I'll just do a couple or 3, and we'll say, you know, there's AND gate 0, AND gate 1, AND gate 2, AND gate 8, if you like. And AND gate 8 will have 3 inputs, X, Y, Z. AND gate 2 will have 3 inputs, X, Y prime Z. And gate 1 will have 3, inputs X, Y, Z prime, and then, or maybe it would be this way, prime, prime, and not prime. And this would be prime, not prime, prime. And then this one would be all prime, X, Y, Z, all prime. So we're basically putting in 0, 1, 2, and 3 as product terms coming in. And the only difference now between that and what we've got is you also want to add the inputs for X0, X1, X2, X8, and then take the whole thing, run it into a summing junction, and that's your multiplexer. So multiplexer is really little more than bunch of AND gates with a summing junction, an OR gate. And that's that. What else? Anything else? We're done with this one. We're going on to homework 7. Is that all right? I am declaring homework 6 reviewed. You should be okay now with homework 6. Let me switch now to homework 7. Let's see now. Let's see, how do we do this? Course content. And edit test. All right. Looks like a few people have tried it already, which is good. Homework 7 came online last night. I think we were starting to do some numbering systems last time. Let's just go back to a blank sheet of paper. Oh. Find a way to keep this camera from falling. So I think we covered a little bit of 2's complement, but just to remind you, and we'll try a 2's complement, a simple one. Let's try a simple one. I'll do maybe it's not so simple. I'll do number 29. Let's start with the hard one, number 29. So it says here, what is the 12-bit 2's complement of the decimal number 1, 2, 3, base 10? And therein lies an interesting thing. I mean, you think about it, 1, 2, 3, base 10 has a binary representation, but when he asks for the 2's complement of the decimal number, what he's really wanting to know is, how do I represent minus 1, 2, 3, base 10? So we can start by computing the binary, right, which we can get through repeated division. So we divide 1, 2, 3, and we get 6 1, and then with 1 left over. And then we get 3, 0 with 1 left over. And then we get 1, 5 with nothing left over. And we get 7 with 1 left over. Then we get 3 with 1 left over. And then we get 1 with 1 left over. And then we get 0 with 1 left over. And by the time we're done, we read from the bottom and go to the top. 1, 1, 1. 1, so that's 4 ones, 0, and then 2 ones. Base 2 equals 1, 2, 3, base 10, unless I've made some sort of error. Let me just check. No, it looks about right. So then you're asked to do this using a 12-bit quantity. Oh, how many bits we got? 1, 2, 3, 4, 5, 6, 7. We don't have 12 bits. So what do we do? Oops, don't write 0. 1, 1, 0, 1. Group it by 4 just to keep things safe. And saying 1, 2, 3, and then a leading 0. Now I need another set of 4 bits to get 12. Doesn't matter if they're all 0. So now I've got a 12-bit quantity, which is what was asked for. And this is a non-negative quantity. But I know how to do 2's complement, so I formed the 1's complement, which means I invert. And then I add 1. And that is equal to minus 1, 2, 3. And let me just check my work. That is correct. That is correct. So what do you think? Was it clear? We had to do a process, right? First we needed the binary using repeated division. Then we used padding in order to get the 12 bits. And then we proceeded to use 1's complement to do the complement of the accumulator, and then increment, and then we get the answer. So that's the procedure. So there's padding with leading zeros. Padding with leading zeros doesn't change anything, except it gives you the 12 bits that you felt you would need in order to be able to form the 2's complement.
Wait, Professor?
Yes.
So is it the first choice? I'm a little confused because I don't see the answer that I'm not reading that other than the first choice.
Yeah, the first choice is the same thing as what I've written, isn't it? It just says 0B, which means it's in binary.
Oh, okay. Thank you.
Yeah. So, yeah, I don't know if you got confused by that, but 0B versus 0X, these are ways in which you can represent binary numbers as literals inside of your computer program, which could in principle be C or C++ or C# or Java. They'll all take literals encoded in this way. Let's try another one. I think this was fun. So this was question 29. Did everybody kind of understand that?
Can you run through it one more time, please? Just step by step.
Sure. So step 1, we were asked to find the 2's complement. So before I did that, I needed the binary version of the decimal number. So I convert to base 2 using repeated division. And then I wrote out the number and set it equal to 123 base 10, only in base 2. And I said, well, he's asking for 12-bit quantity. So then I wrote the same number out in groups of 4, so it was obvious that you needed to pad with leading zeros, which is what I did. Then I formed the ones complement, which means bitwise inversion, and converted all the zeros to ones and all the ones to zeros, hence the inversion thing. Then I added 1, because it's CIA, complement and increment the accumulator is the instruction for the PDP-8. And then I got like a number, and then I went into my answer key and I looked it up. What do you think of that? Does it seem sensible? Or is it... Any questions? No questions? So let's try another one. Suppose somebody says that 0100 base 2, and someone wants to know what is the 2's complement. Well, that in decimal looks like a 4. But if the decimal number of the 2's complement is, let's form the complement, 1 0 1 1, and then add 1, it's 1 1 0 0. But by the time we're done, we're going to get the decimal number, which will be -4. So if you form the 2's complement of some positive decimal number, the outcome will be a negative number. Or, well, unless it's 0, in which case you don't have -0. Right, because if you did 0 0 0 0 and formed the 1's complement, you get 1 1 1 1, and then if you increment, you're back to 0 0 0 0 with a 1 that falls on the floor. So in effect, 0 negated is still 0, which is one of the good things about 2's complement. It doesn't have a -0. We don't want, it's not good to have numbering systems with -0. And that was question number 28. So what do you think of that? Is it sensible? They gave us,
Professor, could you maybe just go through that like one more time? Sorry.
sure, no worries. So question 28, let me go back to 28 on the screen here. What is the decimal number of the 2's complement of 0 1 0 0? So what you want to do is convert 0 1 0 0 into a decimal number, and that is the decimal number 4. And you know 2's complement is going to give you -4. And he wants to know what is the decimal equivalent of -4, and the answer is -4. You don't even have to go through and do the 1's complement and then increment, although you certainly could. Is that all right? People okay with this?
Yeah, I'm good with that. I just didn't realize with all the 1s and 0s that we didn't have to do that.
Yeah. You don't really have to. Not in this case. So here's another one. What is the 4-bit binary number of the 2's complement 0110? So this is question 27. And we wanted to start with 0 1 1 0, and someone says find the 4-bit binary number of the 2's complement, which basically means find the 2's complement. So what do? We do the 1's complement and we get 1, 0, 0, 1. Then we add 1 and we get 1, 0. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. And so I get 1, 0, 1, 0, base 2. So if this number here is 0, 2, 4 plus 2, which is 6, then this number here must be minus 6. And what he's asking is, what is the binary representation of minus 6? And there it is, in 2's complement. And so that gives you an answer to question number 27. What do you think of that? Who got confused by this?
Yeah, I'm
How did you get that at 6 up top?
Oh, somebody said the given 0, 1, 1, 0, base 2. Find binary. This is in question 27, by the way. Find the binary of the 2's complement. So I converted this binary number into base 10 and said this is the number 6, because 0, that's 2 to the 0, 2 to the 1, and 2 to the 2. So I added 2 to the 2, which is 4, plus 2 to the 1, which is 2, and 4 plus 2 is 6. So I said this is a 6, and he's asking me to find the binary representation of minus 6. So I did the 1's complement and got 1, 0, 0, 1, added 1 and got 1, well, 1 plus 1 is 0, carry the 1, and then the 1 plus 0 is 1, and then that's 0, and that's 1, and so that is the 2's complement representation of the decimal number minus 6. What do you think of that? Who got confused? Be honest. Nobody? You guys are getting this? All right, let's try a different one. Try a different problem. Let's try problem 26. Problem 26. What do we got here? It says here, what is the 2's complement representation of the decimal number 7? And it looks like he's asking for it in binary. This is question number 26. So question 26, given 7 base 10, find minus 7 base 2 in 2's complement. So you tell me, how do I approach this problem?
Could you start by writing out the binary for 7?
Sure, let's do that. 1, 1, 1. Is that good? Did I do it?
Yeah, and then you could invert it. Well,
No.
yeah, invert it.
But what about the sign? Where will the sign go? See, this is not enough. If you convert from decimal to binary, it's sufficient. But if your goal is to have room for negative numbers, you'd better put in an extra leading 0. You're gonna need that. Now you can invert it. Now you can write 1, 0, 0, 0. Then you can add 1, and you get 1, 0, 0, 1. And that is the binary for the 2's complement of minus 7. Does everybody see why you needed that leading zero. It's the only way we can use to keep track of the sign SIGN of the number, you see. So you gotta put it in, gotta have it. Who got confused by that one? So let me do another one. I like this little drill work thing because it's sort of a, I don't know, important thing. What is the 8-bit 2's complement of the decimal number 70? So this is question 24. And we want 70 base 10. And apparently we want minus 70 equal to, whoa, minus 70, I said base 10. Base 10 is equal to what in base 2? That's what he's asking. So what do I do first? How do I approach this problem? I'm gonna try to call on some people. How about Eric? What should I do to approach this problem, Eric?
I have an idea.
No idea. Well, how about we convert 70 into binary? Do you know how to do that?
Can we use the -7 that we just found in problem 26?
So you'd like to do this 0, 1, 1, 1, and then what? 0, 0, 0, something like that. That doesn't work for us. Then we gotta do the repeated division. You want to help me with that, Eric?
So then just 35.
Yeah, it's 35 with 0 left over, and then 1, 7 with 1 left over, and then 8 with 1 left over, and then 4, nothing left over, and 2, nothing left over, and 1, nothing left over, and then 0 with 1 left over. So at the end of the day, I get 1, 0, 0, 0, 1, 1, 0. Base 2 is equal to 7, 0, base 10. And that's positive. I'll put a 0 in there just for yaks. Did everybody kind of understand what I just did? You know, first homework, really. And then let's form the 1's complement. So now I got 1, 0, 1, 1, 1, 0, 0, 1. Then we'll add 1. And I get 0, carry the 1, 1, 0, 1, 1, 1, 0, 1. And that is base 2 minus 70 base 10. Let's see if I got that right. I wanted an 8-bit 2's complement. An 8-bit 2's complement. How many bits do I have now? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's correct. I got 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0. Yep, that's correct. Yeah, I got it right. Yay. That's good. That's good. All right, so I'll come back to my original question. Who's confused? Everybody on board with this stuff? I'm glad you're such experts. So then what we'll do, let's go to 23. It's good we have this drill work here because then I can call out people and see what happens. This was question, which question was this? This is question 24.
I have a quick question.
Yes, sir.
So the second to last number, so the 0, how come it turns into a 1 with the output?
This one?
Yes, that one.
So at 1 plus 1 is equal to 0, carry the 1. 1 plus 0 is equal to 1. So in other words, 1 plus 1 is equal to 1, 0, because we don't have a numeric representation for 2 in binary. So 1, 0 is actually equal to 2 in binary. So when we add 1 plus 1, we get 2 in binary. So that's why we carry the 1. Does that sort of make sense? You do the same thing if you exceeded the base of anything. If you said 9 plus 9, right, you'd probably say, oh, I've got to do a thing, and then I have to do a carry, and then you'd get an extra digit. You could do it with, well, let's see. Suppose you had 9 plus 1, right? What really happens? You've exceeded the base of 9. It is equal to 10, so you go 1, 0. But what you've really done is you've said 9 plus 1 is equal to 0 times 10 to the 0 plus 1 times 10 to the 1. That's positional notation for the decimal number 10 in base 10. You can see it's base 10 because the base of the exponent is 10. You could do the same thing in any radix. Whenever you exceed the number of symbols in the radix, you've got to generate a carry. Did that answer your question?
Yes, thank you.
Okay, very good. My pleasure. So let's do another one. So we did 24 over here. Let's going backwards here. So let's try 23. I'll just grab a little area in here in the paper. 23. What is the 8-bit 2's complement of the decimal number 100? Okay, base 2. That is a decimal. No, I'm sorry. That's not decimal. Base 10. Base 10. So it's actually not 100 is a totally different number, base 2, than it is base 10. It says 2's complement of the decimal number. So the decimal number is 100. The 2's complement is going to be minus 100. But he wants to know what it is in binary. This would be question mark in parentheses 2. So how do I write? Right. It says, what is the 2's? I'm going to reread this. What is the 8-bit 2's complement of the decimal number 100? And your candidate answers are all written in binary. So we're looking for a base 2 answer to what the representation is for minus 100. And it's going to be 8-bit. So what do we do? How do we approach this problem?
Do we divide first or?
Yeah, let's convert to binary. That sounds good. I like that. So we get 5, 0, with 0 left over. Get 2, 5, with 0 left over. I get 1, 2, actually, goes in once with 0 left over, and then 2 with 1 left over. Yep, I got that. Learn to divide by 2. 6 with 0 left over, and it's 3 with 0 left over, and we do it again. 1 left over, 2 goes in here, 0 with 1 left over. And so I think we have 1, 1, 0, 0, 1, 0, 0, base 2. And if I were going to figure out if this was correct, I'd say 0, 1, 2 to the 2, which is 4. 0, 1, 2, 3, 4, 5. That's 2 to the 5. And that's 2 to the 6. So this would be 32. This would be 64. And then 64 plus 32 is going to give me 96 plus 4 is going to give me 100. So that worked. I got 100 in base 2 right in through here, 100. So I checked my work. Now, it says here I have 8-bit numbers. So let's look at this. 1, 2, 3, 4, 5, 6, 7. It looks like I need a leading 0 to get an 8-bit number. 0, 1, 1, 0, 0, 1, 0, 0, base 2 is equal to 100 base 10. And now we form the ones complement. 1, 0, 0, 1, 1, 0, 1, 1. We add 1, and we get 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. This becomes a 1, 1, 1, 0, 0, 1. In parentheses, base 2 equals minus 100 in parentheses, base 10. And we're grouping 4 bits at a time, and that gives us an answer. And it checks with the answer key too. And that's question number 23. What do you think? You guys getting it now?
Sure.
Cool, cool. Let's take a look and see what else we got. I want to make sure you guys are getting this. You know what I need to do is zoom out just a little. Oh God, I went too far. All right. Let's try and do, I'll leave a few of these for you. Let's try to do this one. So this is what you call a full adder. It's got to carry in, it's got to carry out, it's got a summation input A, B, and a summation junction output S. Call it S0, A0, B0. And now we have what's called a full adder. That's a full adder. So then the question is, well, how does that work? Well, if you're adding 2 bits together, 0 plus 0 gives me 0. 0 plus 1 gives me 1. 1 plus 0 gives me 1. 1 plus 1 gives me 0, but I have to carry the 1. So I got to carry. So if I'm going to do it with a truth table, I got to have a carry in and 2 bits coming in. So what we'll do is we'll write carry in A0, B0. And now we have 2 outputs, carry out and sum out. And sum out and carry out both have to be 0 when the inputs are all 0. Here and here, we just have no carry. But here and here, it looks like we got a carry out with no sum. And here we just have a sum with no carry. And here we got a carry out with no sum. And here we got a carry out with no sum. And here we got to carry out with the sum. And so now we have 2 different functions, one for the sum and one for the carry. And we can optimize those functions if we like. Turns out the summing junction is going to be a 1 when there's an odd number of 1s. And so what we can say is the summing junction, Cn, A0, B0, is the exclusive OR of carry in, carry A0N and B0N. And the AND gate is going to be true if A0, B0 is true, if actually, if you have more than two or more of the inputs are true. Two or more of the inputs are true, the output is going to be true. So what you could do, if you wanted to, is you could do a truth, well, do a K-map, whatever. K-maps are good. I like K-maps. And then for C0, you would just write the numbers at the onset in 3, 5, 6, and 7. Everything else would be 0. And that means that you would have a loop here, a loop here, and a loop here. Now, what would happen if you didn't have a carry-in? For your first cell in your adder, you have what they call a half adder. No carry in, but you got to carry out. So now, without a carry in, this just became a whole bunch easier, right? Because now A0 and B0 are just 2 bits for the half adder. You still need a sum out and a carry out. But turns out they're a good deal easier to write because now the sum is simply an exclusive OR of A and B. And carry out is just the AND of A and B. And so this is the circuit that came from homework number 21. And it says, the above is a half adder because A, it has no carry in. That's what makes it a half adder, as you can see. So when you're adding binary numbers using hardware, you can start with a half adder because it needs no carry in. But then as soon as you get beyond the half adder, you got to expand the truth table a little bit and include the carry in. How does that grab you? Who got confused on this one? It's clear, right? Because you've got a 3-variable K-map, which can optimize for something like C0. And you've got a way to implement using this minimal sum of products form your full adder. And you can figure out what those product terms are, I'm sure. Did anybody get confused by that? All right. Let's see what else we got in this homework here. It's a relatively long homework assignment, I think, because we're going on for 30 questions. Yeah, here's one. It's question number 16. Let's take a moment and see if we can do that. So in question 16, it says, write the 2's complement for the 5-bit binary number base 2. And so we do the 1 0 1 1 0 thing. We add 1. And that is the minus version of whatever that is. We can figure out what it is, right? 0, 1, 2, 3. So that's 2 to the 3. That's 8. And 2 to the 0. So this whole thing is 9. So this must be equal to minus 9. And in fact, this is a correct answer for question 16. Now, who got confused on that one? Nobody? That's good. That's good. Let's see if we got any more questions in here that we should do. All right, so here's a good one. You'll like this. In let's see if I can. Make it just a little bit bigger. There we go. So, Fleming. It was in the late 1800s, maybe early 1900s, Sir Ambrose Fleming was employed by Samuel Morse, who basically controlled telegraphy through his patent. When you were in the Titanic, you didn't go to the radio room. You went to the Morse room. Morse had licensed operators, had full control of the patent, and he was looking for a way in which to communicate using Morse code over the Atlantic. So he needed a transatlantic radio-operated telegraphy device to receive. Now, normally what you do is you get an antenna, big antenna, and then you run it through what's called an inductor. Right? Usually you can make one of your own using like an empty Quaker Oats container wrapped with enamel wire. Then use a little sandpaper, and you can scrape a tap off of the wire and change the inductance, which changes how it resonates for different frequencies. That's your tuner. And then what you do is you have to go through what's known as a rectifier. And so you give it a little diode. Now the diode has a bit of a voltage drop to it. And then the voltage that comes out can go into a very sensitive speaker, which is basically built into your headphones so that you can hear what's coming out. Now what they used to do is they used to use a piece of germanium and what's known as a cat's whisker. They take a safety pin and they cut off its head, and they'd let the pin part actually touch the germanium crystal, and that would make a point contact sensor, which had the behavior of a diode, so voltage would only travel through in one direction. What Samuel Morse needed was a way in which to make this more sensitive, Turns out Edison came up with a discovery that if you had what's called a plate and some sort of a filament inside of a vacuum, that you could actually have electrons boil off and you could develop conductivity from one conductor to the other. He called it the Edison effect. He didn't know what to do with it. Later, Sir Ambrose Fleming said, you know, you can use this as a highly sensitive inductor. And this became known as the Fleming valve. In the UK, tubes are called valves. And so the first rectifier was known as a thermionic diode. Thermionic because it's thermal, because the filament is hot. Ionic because there's a stream of ions flowing from the filament into the plate. And this was patented in 1904. Over 100 years ago now. Trouble is, here we know the voltage drop for a silicon diode is something like 0.7 of a volt. But the question then becomes, how do we find out what the voltage drop would be in a vacuum between the filament and the plate? And the answer is we don't know. You know, it all depends on how much air is in here, the permeativity electrically of the space. Nobody really knows. And sometimes they call this Fleming valve a kenotron. Everything had a TRON at the end. Electrons, protons, kenotrons, morons. So they all had, you know, the sort of question of what will the voltage drop be? Turns out it's exquisitely sensitive, much more sensitive than the solid state device, but it's huge and it takes up power and it's hot. People kind of want to see if they could avoid it, if at all possible. So that's a non-solid state diode. Right? They didn't have like silicon diodes then. I don't think they had silicon, much silicon anything back then. What do you think? Is it clear? So now you know about Sir Ambrose Fleming and the so-called Fleming valve. And now,
Professor,
yes.
that was number 12 that you just went over, correct?
Yeah, just a minute, please. Yes, that was number 12. That was number 12.
Thank you.
Sure. Now I'm going to do one that's not a number because I want you guys to have a look at it. I wonder if you can see it. Can you see it? I guess you can't see it. What if I turn this off? Now you can see it. There you go. So this is a chip with a little window on the top. You can kind of see the chip inside, and it's bonded to these little areas in here around the die, and then they get wired up to the little legs out on the outside. What is it? Anybody know? Well, we're out of time, so I'll tell you. It's a electrically programmable read-only memory, also known as an EEPROM. And what it does is it lets you write the data into the chip, and it will store the data indefinitely. And then when you want to erase the data, you get a little, oh, I'm writing on it. You get a little ultraviolet light, and you hit it with the UV light, and it erases the chip, and then you can program it again. Electrically, it is non-volatile, programmable read-only memory. So it's read-only memory. It's not volatile. It's programmable because you can program it in the field, and it's erasable because you can use an ultraviolet light to erase it. In fact, you could even leave it on a sunny window. So what people do is they cover up the window with a little piece of tape to keep it from getting erased. And that is an EEPROM. And you program these things with what's known as an EEPROM programmer. And that gives you it gives you non-volatile memory, which you can then proceed to use. I had BASIC stored on this for a little microcontroller at one point. You could plug it in. You could just run the BASIC language on the microcontroller. Boots right away. It's kind of cool. All right, so that's what I got for you for today. It's a lovely day out. I think it's going to get warmer this week. Stay safe, and thank you for your attentions.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank
Thank
you.
you.